Sorry.
Introduce you so you don't have to introduce yourself.
Sounds good, yeah.
You ready for me to start introducing you?
Yeah.
All right, everyone. So for the next session, we're happy to have David Poland. He's been around last week, so you probably got to chat with him, one of the scientific organizers as well as a lecturer. And we are delighted to have him telling us about frontiers of the conformal bootstrap.
All right, thank you very much. So so my lectures are going to be telling you something about the conformal bootstrap. I thought I would start with just kind of a broad picture of the goals of this research program. What are we trying to accomplish? What are we broadly trying to do? And okay, so at zeroth order, the goal really of any of the Bootstrap programs that you've heard about is to solve or perhaps constrain strongly coupled physical systems. And okay, so that's a great ambitious goal. And the way the Bootstrap tries to accomplish this is kind of a general philosophy, which is to, first of all, focus on physical observables, things you can measure. And then try to come up with some way to constrain those physical observables, perhaps using symmetries, perhaps using other kind of fundamental consistency conditions. Okay, so we're going to try to constrain them using symmetries. And consistency conditions. And for us, what those are going to mean are, first of all, imposing some kind of positivity property on our system. So this is sometimes called unitarity. Or more generally, there's a form of positivity we can impose. And then another constraint that we'll talk about later is called crossing symmetry. And these together form a very interesting set of constraints that are hard to satisfy collectively. Okay, so now there are lots of different kinds of bootstraps. You've seen some of them in this school previously. So first of all, let me just say that there are many incarnations of the Bootstrap. So I'm going to be focusing on what's called the conformal Bootstrap for CFTs in d dimensions, and I'm mainly going to be talking about CFTs in more than 2 dimensions, because in 2 dimensions, there are lots of special things that can happen. So in particular, another version of the Bootstrap that you may have heard about is called the modular Bootstrap. This is specific to 2-dimensional conformal field theories. You ask, what if you put a 2-dimensional conformal field theory on a torus and require that its partition function is invariant under modular transformations of that torus, you get some interesting constraints. Another version of the Bootstrap is the S-matrix Bootstrap, which is aimed at trying to understand the S matrices of gapped quantum field theories in general. Then there are even more kinds of bootstraps. There's a lattice bootstrap for lattice systems. There's an effective field theory bootstrap. You heard last week about a kind of bootstrap for matrix quantum mechanics. And the list kind of keeps going. And all the way, there's a cosmological bootstrap. And it's kind of continuous with various problems in pure mathematics as well. So for example, the sphere packing problem is a kind of bootstrap problem. In math, you can ask questions like, can you place bounds on the eigenvalues of the Laplacian on hyperbolic manifolds? This is another kind of bootstrap problem. Okay, so, and lots of these problems have structural similarities. They all often involve combining something like positivity with something like crossing symmetry. And the first thing I wanted to say, just kind of generally, is that all these different bootstraps have a lot to learn from each other. And it's very much worth your time getting familiar with the different versions or incarnations of the bootstrap idea and asking what ideas you can import from one arena into another. And that's been a very fruitful avenue for making progress in this general direction. Okay, so now my lectures, as I mentioned, are going to focus on the conformal bootstrap. And so I'm going to start off just mentioning some kind of basics about conformal field theories, and in particular, some useful technology for talking about spinning correlation functions in CFTs. Which show up in various contexts, but in particular in the kind of cutting edge conformal bootstrap studies that are going on right now. 4-point functions of, say, spinning operators like the stress tensor are playing an important role. So it's important to understand how do you talk about them. Another important ingredient in the Bootstrap program are these special functions called conformal blocks. They show up when you formulate the crossing symmetry consistency conditions, and one has to know how to compute them, what properties they have, and so on. So I'm going to tell you a little bit about our modern understanding of conformal blocks for d-dimensional CFTs. Then my main focus is going to be on kind of putting these ingredients together to compute constraints and interesting bounds on CFTs. I'm going to focus most of my attention on 3D CFTs, where a lot of progress has been made in recent years. In particular, one of the more recent cutting-edge Bootstrap studies has been combining 4-point functions of scalar operators with the stress tensor. And this has, for example, led to some of the most precise results for the critical three-dimensional Ising model. And so I want to tell you about the ingredients that are going into that cutting-edge study. OK, and then that's going to take the bulk of the time. If there's time, I'll talk a bit about some future directions that I've been thinking about. Yeah, question.
If people have the compact form of three-dimensional conformal block, or we just have some infinity series of these conformal blocks?
Good question. Well, I'll talk more about it later. But the short answer is no. We don't really have a nice compact form. There is kind of a compact expression you can write down, written in terms of a fractional derivative acting on some kind of hypergeometric function. That's sort of a closed form expression, but involves a fractional derivative, which is really like some integral. But also in various, in various kind of special situations, we do have closed form expressions. Like, I'll mention it later, but if you look at the conformal blocks along the diagonal, this is a certain kinematic configuration, then we do have closed form expressions. So we'll get there later.
Can I ask a motivational question?
Yeah, motivational.
So understanding this, getting more better bounds on some correlators or understanding these correlators better,
Yeah.
is there like a killer app, like some physical phenomena that we would be able to understand better by doing, like getting better and better at bootstrapping CFTs, or like in 3D, maybe understanding something about the phase transition in water or something? Like, is there like a killer physical observable that we want at the end of the Bootstrap program?
Okay, yes, the question is what is the application? I mean, so, okay, so one, obviously there are some things that are easier to measure than others in real world systems. Typically people will measure, the leading critical exponents in some system like, which has a critical point. So first of all, going to these larger Bootstrap systems gives you more precise results for those exponents that are easy to measure. And then there are quantities that are a little harder to measure, OPE coefficients. These spinning correlators give you access, let you say things about OPE coefficients that you didn't have access to before. Some of those could be measured. One example is, for example, that maybe Tom will talk more about, are energy correlators. 4-point functions involving the stress tensor give you access to the information that you need to compute energy correlators in these theories, and that's something that you could, in principle measure.
Maybe can I rephrase a little?
Yeah.
Maybe is there like a list of things experimentalists would like to get out of the Bootstrap program? like something, because they are also computing some critical exponents, and we are trying to match that with our Bootstrap results. And but we can get much more accuracy than say an experimentalist can. But is there like some new things that they would want from the program that would help them in doing some experiments or measuring something in the lab or something like that? Like my flavor is that are there new things that we would learn from getting these bounds tighter and tighter?
Yeah, well, so it really depends on which theory you're talking about. So for some theories, the current version of the Bootstrap is very good at isolating these theories and computing its data very precisely. And there, the Bootstrap program is kind of ahead of experiment. In other theories, there are various experimental results which you'd like to understand, and the Bootstrap hasn't yet figured out how to isolate those theories and compute things about them. And so one of the motivations for going to larger Bootstrap systems involving spinning correlators and so on is to actually just get to the point where you can isolate the theories in the Bootstrap and make precise predictions, which could then be compared with experiments. So maybe a little later on we can revisit this question. Okay. So, okay, good. Okay, so let's start. By talking about conformal field theories. And so the first thing you want to ask when you're talking about conformal field theories are what's their symmetry, and a d-dimensional CFT has SOD plus 1, 1, or SOD, 2 symmetry. So which one of these is the right symmetry group depends on whether you're in Euclidean or Lorentzian signature. So this is for Euclidean CFTs. This is for Lorentzian CFTs. So notice we're talking about a d-dimensional theory. In the Euclidean case, we'd have d spatial dimensions, but the symmetry group is kind of d plus 2 dimensional. And so how do you understand that? Well, for example, here there's one direction. This is like the Lorentz group in d plus 2 dimensions. There's one direction that's not compact. And what does that correspond to? Well, that corresponds to doing a scale transformation. So if you do a scale transformation, you zoom in or zoom out, you can kind of keep doing it as much as you want. You could zoom in arbitrarily far. You'll never get back to where you started. That's a non-compact direction of the symmetry transformation. And in general, we can kind of write down the generators of the symmetry. There are translations, p mu. There are rotations, m mu nu. There are transformations called special conformal transformations, k mu. And there's the generator of dilatations or scale transformations. So translations, rotations, special conformal transformations, and dilatations. These all live together inside of an algebra. Let me not write that down right now, but let's just do a quick counting of the number of generators to make sure it kind of matches with this picture of the symmetry group. So okay, so in general, if I'm in d dimensions, I have d different translations I can do. have d minus 1 over 2 rotations. This is encoded by an antisymmetric d by d matrix. I have d special conformal transformations because these are also encoded in a vector, and 1 dilatation. And okay, you add these numbers of generators together in Mathematica, type full simplify, and what do you get? D plus 2 times d plus 1 over 2, which is the number of generators of the d plus 2 dimensional Lorentz group. Yeah.
So you said that there's like this one non-compact direction.
Yeah.
But what about the translations?
Right. So yeah, of course, translations in flat space are also not compact. But the statement is that if there's this nice map you can do between flat space and the cylinder. This is what you do when you do radial quantization. And in the radial quantization picture, there's only one non-compact direction. So that's how you make the precise connection. Okay, so so we're going to be talking a lot about operators in conformal field theories. So these live in conformal multiplets. And a conformal multiplet consists of what's called a primary operator at the bottom of the multiplet, and then together with its descendants. So here I'm going to write down an operator at the origin. Its descendants are derivatives of the operator at the origin. So here I'm going to start writing down some descendants. Dot, dot, dot. Okay, so this is a primary, and these are descendants. And the basic picture is that if I start with a primary operator, and the kind of definitional property of a primary operator is an operator which is annihilated by the special conformal generator. Then what I can do is, if I act on a primary with P, the translation generator, I'll start getting derivatives of that operator. And so P takes you from here to here, or from here to here, etc. On the other hand, if you act on a descendant with K, then it takes you in the other direction. Okay, so K will take me from here to here, or from here to here, and then if I act with K again, I get 0 because I have a primary. Okay, so this is the basic way. One basic way we're going to organize the operators in our conformal field theories. We're going to talk mainly about the primary operators, and the properties of the descendants of those primary operators can be obtained by acting with P in various ways. Now the primaries themselves are labeled by some quantum numbers, in particular the scaling dimension which is delta, as well as some representation under the rotation group. Okay, and okay, there are different, depending on how many dimensions you're in, there are different possible representations of the rotation group. These are kind of different ways of talking about possible eigenvalues under the M generator. For many purposes, we can primarily talk about what are called spin L representations, which are traceless symmetric rank L tensors. Okay. Of course, there are other things in life other than traceless symmetric rank L tensors. You can have antisymmetric tensors. You can have spinors, which are representations of the double cover of the rotation group, etc. For most of the purposes of these lectures, we can focus on the spin L representations. And so, so we can write down some operators in our theory, which has some indices collectively labeled by I. That this I might be shorthand for L indices, which are traceless and symmetric, for example. And then the other thing to say is that if I want to have write down an operator at some position x, that's always related to an operator at another position, like the origin, by a translation. So for example, we can write down general. If I act with a translation on an operator at the origin, I could get an operator at a different point x. Okay, so just as in Tom's talk this morning, the basic observables we're going to be talking about are correlation functions of local operators like these. Yeah.
Just so I get my convention straight, it should be e to the ix, but here is the I hiding in the.
Yeah, so that's just a question of how you define whether you absorb the I into your generator or not. I don't think that convention choice will matter for my lectures. But yeah, if yeah, you can always absorb the I into the definition of the generator, which makes some formulas nicer, but then you have to worry about, you have to think carefully about the properties of your generators under Hermitian conjugation and so on, which depends on which signature you're in and what kind of quantization scheme you're doing and so on. Okay, that's not going to be so important for us right now. Okay, so we're gonna start thinking about correlation functions of local operators. So objects like this with n different operator insertions. Each one might carry some indices which tell you about its spin representation. Each one's at a different position. I'm primarily going to be focusing on Euclidean signature, where the operator ordering doesn't matter because the operators all commute with each other. So these are nice, well-defined objects. And so a very basic question you might ask is, how does conformal symmetry constrain these objects? For like scalar operators with no spin indices, it's not too hard to just kind of brute force write everything down explicitly, try to construct combinations of the x's that are invariant under all conformal transformations. Once you start dealing with operators with spin, it's useful to have some kind of more powerful formalism for writing down all of the conformally invariant structures that could show up in these objects. And there are kind of two basic approaches one might take to doing this, which have advantages and disadvantages. The one I'm going to be focusing on today is called the embedding space. The basic idea behind the embedding space formalism is that instead of working in d dimensions, you can work in a d plus 2 dimensional space where this conformal symmetry, like S of d plus 1 comma 1, is linearly realized. Okay? And that makes studying the consequences of the symmetry much, much easier. There's another approach you can take to thinking about these correlators, which is called the conformal frame approach. Where what you do is, instead of working in some higher dimensional space where you try to make all the symmetries manifest, you use your symmetries up as much as possible to fix the positions of the operators. You can always do conformal transformations to move around the positions of your operators. And so you kind of use up all of your conformal symmetries to fix positions of operators and then see what's left over at the end of it. Depending on what you're doing, one of these approaches might be more useful than the other. The first one has the advantage that the symmetry is completely manifest. It's pretty easy to work with. Things like imposing conservation constraints of operators is easy to do in the embedding space, as well as permutation symmetries and so on. On the other hand, it has some disadvantages. For example, there can be redundancies between embedding space structures, which you have to think carefully about, and those go away when you're working in the conformal frame approach. And kind of both of these methods are used in different ways in the literature on the Bootstrap. Yeah. Is the embedding space method related to holography? So you can use this method completely independently of any holographic interpretation of your CFT. So you don't need your CFT to have a holographic dual to use this formalism.
Would it be kind of useful and
Yeah.
more insightful to try to
Yeah. So it's also the case that the isometries of anti-de Sitter space are the conformal group. It's the same symmetry, SOD plus 1 comma 1. And you can construct anti-de Sitter space by also embedding it within this embedding space And so you can make a connection. You can write down correlators in ADS using the same kind of formalism. And so it's kind of a useful technology in the context of holography as well. Yeah.
Can you clarify why conversion functions are observables? Because usually in QFT or graph theory, observables are defined asymptotically. So why are these
In a quantum field theory, correlation functions of local operators are observable. You can create local excitations of your theory and ask how correlated that is with other local excitations of your quantum field theory, and that's something that can be measured experimentally. So you don't need to talk about asymptotic quantities in the context of quantum field theory. Gravity is a different story, but here I'm focusing on quantum field theory. Okay, I need an eraser. Okay, so let me tell you a little bit about the embedding space. There are different versions of this idea that have a long history, even going back to Dirac. The version I'm going to tell you about was developed in this this paper titled "Spinning Conformal Correlators," and it's kind of one of the more practical implementations of this embedding space idea. So I want to tell you about it for that reason. The idea is that you kind of set up this formalism in a D+2 dimensional Minkowski space. Okay, there are different. Okay, we can write down the metric of Minkowski space. It's kind of convenient to use some light cone coordinates. X plus and x minus, so that so the metric is kind of off diagonal in the first two entries and then diagonal in the other entries. And okay, and so the basic identification that we're going to try to make here is that a point x mu in d-dimensional flat space, which are ultimately that's ultimately the space we're trying to work in, gets identified not with a point in this d plus 2 dimensional space, but with a null ray. And so okay, so null, of course, means a d plus 2 dimensional point that satisfies p squared equals 0. We can kind of visualize. We can visualize this by drawing the p plus direction and the p minus direction, and in the space, and a general null ray might sit on this null cone. Sorry, this is a null. This line is supposed to be a null ray, which exists on the null cone, which rotates around the central axis. And so a point on a null ray, we can kind of simply parameterize up to some overall constant lambda as 1 x squared x mu. Okay, so this is a d plus 2 dimensional vector, which squares to 0. Okay, you can just check that p squared equals 0 using this metric. And depending on my choice of lambda here, that tells me where I am this null ray. Now, on top of that, it's nice to think about specifically the point with lambda equals 1, which is sometimes called the Poincare section. Okay, so that, in this picture, lambda equals 1. This corresponds to the intersection of some curve, the Poincare section, with our null ray, and isolates one point in the higher dimensional space. And the nice property of going to the Poincare section is that my higher dimensional point is equal to x mu if I evaluate the d components beyond the first two. Yeah.
P plus and P minus are slightly confused. What space?
Sorry, so
The axis P plus P minus.
yeah, so P vector, PA, represents a point in d plus 2 dimensional space, and P plus and P minus are the first two components of that vector. Okay. Other questions?
I guess I'm just wondering, so in this identification, always, oh, no, so, I'm good.
You're good? Okay, great. Any other questions?
Maybe
Yeah.
you're going to get to this, but isn't the tip kind of problematic? It's like, which ray would you associate the tip of the code to?
Oh, which ray do you associate the tip of the cone to? Yeah.
If you're at lambda equals 1, you're not at them.
Yeah, exactly. So it's not an issue on the Poincare section. Of course, you could get there if you set x equals 0 and took lambda to 0, but we don't need to really worry about.
It's not important.
it's not important because we're always going to be going to make connections to physical space. We're always going to be going to this Poincare section, where it never shows up. Okay, so let's start to understand why this formalism is useful. So for example, we can start thinking about invariants, SOD plus 1 comma 1 invariants that you can build in this higher dimensional space and ask what they correspond to in d-dimensional space. And so, for example, if I have 2 points, I can construct an invariant by contracting them with each other. Evaluate it on the Poincare section. And what do you get? Okay, so this is kind of a straightforward exercise. Just contract 2 different p's of this form with each other. And you get 1/2 x1 squared minus 1/2 x2 squared plus x1 dot x2. And up to an overall constant, minus 1/2, this is x1 minus x2 invariant square in d-dimensional space. Okay, so this gives you, if I take p1 dot p2 in the embedding space, it gives me the difference between the x1 and x2 vectors and computes their magnitude squared. Okay, so this is, sometimes we'll use this shows up a lot, so we'll use a shorthand that this difference between vectors, magnitude squared, is x12 squared. All right, so something very nice happened. We took the dot product between these embedding space vectors, and we got a translation invariant quantity. We got a rotationally invariant quantity. And so it preserved many of the symmetries that we're interested in. Now, it's not, this is not a conformally invariant quantity. It's not invariant under a rescaling of x1 minus x2. Yeah. D-dimensional. Yeah. So this is x1 minus x2 mu, x1 minus x2 mu, where these mu is the d-dimensional index. Okay, so we got a translation invariant quantity, we got a rotationally invariant quantity. We didn't get a fully conformally invariant quantity because it's not invariant under scale transformations. That's related to the fact that in general, if I do an SO d plus 1 comma 1 transformation that corresponds to a dilatation, a scale transformation, in general, that takes me, it performs some kind of rotation on this vector, but in general, it takes me off of the Poincare section. Okay, so it'll, and then I have to do an additional rescaling to bring lambda back to 1. Okay, so the effect of that additional rescaling is what you're seeing here when the result of this is not a scale invariant quantity. But it's scale invariant up to a rescaling. Okay, so any questions? Okay, so now let's start introducing some operators in this embedding space. And we're going to be interested in describing spin L operators. In our d-dimensional CFD. And so what we're going to do to describe these operators is we'll introduce an embedding space operator, which contains this object. Okay, so here's my embedding space operator. It's going to be a function of the embedding space position P, as well as I'm going to introduce an auxiliary polarization vector Z. And what this auxiliary polarization vector does is it's contracted with each of the L indices of my operator. Okay, so now, of course, in d-dimensional space, I could also introduce a d-dimensional polarization vector, which is contracted with these indices. And this is a d plus 2-dimensional object, which is supposed to contain that d-dimensional polarization vector. In order to have this Z contain the same information as a d-dimensional polarization vector, we can impose some constraints on it. And so in particular, we're going to impose two constraints. First, we're going to say that it's null, z squared equals 0. And we're also going to impose that it's transverse to the position of the operator. So z dot p equals 0. If I impose these two constraints, then the polarization vector can be written in this form, okay, where the RD components of the polarization vector are just some d-dimensional polarization z mu with d components. And the other two components are completely fixed by these two conditions that we've imposed. Yeah.
So x dot z is like the mu nu contraction with z, right? Like there is some.
Yeah, x mu z mu. These are the d-dimensional objects.
And x mu is what appears as p mu.
X mu is the same x that appears inside of P. Yeah.
What is null?
Why is it null?
Yeah.
Um,
Like this permutation, why is the permutation null? Like if I use the metric, I don't get 0, do I? Don't I get set squared in the d-dimensional space?
this z is also null.
Ah, okay.
Yeah.
But like that's Euclidean C, right? So it's complex set. Like I mean, the metric of views is Euclidean, right? It's positive definite.
The metric on mu is Euclidean, that's right.
Yeah. So the C variable Or is this just some formal trick, so we don't need to think about that at all?
Yeah, you can make this complex. Yeah, that's right. To describe a null d-dimensional polarization vector.
Okay,
Yeah,
thanks.
yeah, yes. Yeah, good. So, so in general, this OA object contains more components than just O mu that we're trying to describe. What we want to have happen is when we evaluate A at A equals mu, pick the d-dimensional components, then we recover our d-dimensional spin L operator. But in order for this object to contain the same information as O mu, we need to impose some constraints on it. Okay, so that's what I'm going to talk about next. And so this O, we're going to impose some constraints. And the two constraints that we're going to impose is first that it's homogeneous. In that if I rescale P or if I rescale Z, then I get the original operator back up to some rescaling factor. Okay, so the homogeneity property when I rescale P is related to the scaling dimension of the operator, and the homogeneity property when I rescale the polarization is related to the spin of the operator. Okay. Another way to say this is that to describe a spin L operator, you can think of this O as being a rank L polynomial in Z. And that's what gives you this homogeneity property. The other condition is that it satisfies a transversality property, which I can write as O of P Z plus beta P. Okay, I'm shifting the polarization vector by something proportional to the position, and we're going to demand that it's invariant under such a shift. Okay. Another way to encode the same property is that P dot ddz of O vanishes. Okay, if I take a derivative of O with respect to Z, it frees up an index on O. Then if I contract that index with the position, then I'm getting 0. So we're saying that this embedding space OA field is transverse with respect to its position. Okay, that's one of the constraints that kind of reduces the number of degrees of freedom inside this embedding space operator so that it matches our d-dimensional operator. Okay, so the claim I'm going to make, and I'm not fully proving this for you, but I want to give you the claim, is that if you define an embedding space operator O of PZ with these properties, that it's homogeneous in both P and Z, and that it's transverse, then if you extract the components of that embedding space operator corresponding to the mu components, the d-dimensional components, then you get an operator that transforms as a conformal primary with dimension delta and spin L in d dimensions. Okay, so let me just give you this claim. Restricting this O to the Poincare section, lambda equals 1. And if I extract O of mu 1 through mu L by taking the appropriate components of this O, you get an object that transforms as a conformal primary of dimension delta and spin L. Okay, so this takes a bit of work to prove this statement. That's all done in this paper that I mentioned at the beginning. But this is kind of the lightning summary of the construction. So if we work with embedding space operators that are homogeneous and transverse, and write down embedding space structures that satisfy these two properties, then we will get d-dimensional correlation functions that transform as conformal primaries of the appropriate dimension and spin. Yes?
If we go to like some specific theory, is it clear this map is subjective to all the primaries, or will we potentially miss some?
Well, the idea is for any conformal primary, you can uplift it to an embedding space operator. Now, which embedding space you're working in depends on the kind of operator. So, for example, this formalism I developed here, doesn't work for spinners, and we need to do more work to understand how to describe, say, antisymmetric tensors. But at least for the spin L operators, you can always uplift a CFT operator to an embedding space operator with these properties. Is that, yeah, yes?
If I want the O to be a spinning descendant, does the O still hold?
If you want O to be a spinning descendant, does the property still hold? I think no. I think you need to modify. I think this is too strong because this construction will guarantee to give you something that transforms as a primary. So you need to relax these conditions to talk about
But do you like explicitly
descendants.
use that it's annihilated by K? Like I would just enforcing that under the conformity it picks up delta and L respectively.
Are we imposing that it's annihilated by K? Not explicitly, but implicitly, it's true when we demand these properties. So,
But I mean that
because for example,
like variance under like
yeah.
scaling and rotation, which is also true for descendants, right? Where delta would be appropriately lifted.
Yeah, that's right. Okay, so let me let me think about what precise statement you can say for descendants, because I'm not completely sure on the spot. Thanks. Any other questions?
Maybe one more question.
Yeah.
The tracelessness of these reps, do they come from the fact that set mu also squared to 0? Or
Yeah.
where does that come from?
Yeah, that's right. So so this whole formalism, including incorporating the fact that the polarization squares to 0, that all kind of automatically encodes that these are symmetric, traceless tensors. So it's kind of a very elegant way to encode those constraints. Yeah.
This little z would then correspond to the helicity of the external states in the.
That's right. Yeah. 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 So for any of these d-dimensional operators, you can always contract their indices with some d-dimensional polarization tensor or vector, and it tells you about the helicity. Exactly. Okay. So let me tell you a little bit about how you use this formalism.
We're about 10 minutes left.
Thanks. Okay, so let's just look at some examples. Okay, and we can start with the simplest thing, which is a one-point function. And okay, so now you ask, what could I write down to describe a one-point function, this embedding space operator? And whatever I write down has to be homogeneous in this way. It has to be transverse in this way. And I also need to keep in mind that p squared equals 0, because I'm talking about null rays, and my polarization vector z squared equals 0 and z dot p equals 0. So there's basically nothing I can write down on the right-hand side built out of p and z that doesn't just vanish. And so the only option here is really just a constant. Now, a constant is homogeneous with delta equals 0 and L equals 0. And so what we've just shown is that the only way to write down a CFT one-point function and have it be non-zero is if delta and L equals 0, or equivalently, we're talking about the identity operator. An O with non-zero delta or L, you can't write anything on the right-hand side. That doesn't just vanish. Okay, so now let's go to a two-point function. And let's just look at spin 0 first. Okay, so now things start getting a little more interesting because I'm allowed to take p1 dot p2, and that doesn't necessarily vanish. And so up to some overall constant, I can write down p1 dot p2 raised to some power. And p1 dot p2, 1 over p1 dot p2 raised to the delta power is homogeneous with dimension delta in both p1 and p2. And so this is kind of the only object we can write down on the right-hand side. I put this -2 here, by the way, because of, let's see, is it still, to account for that -1/2 up in P1.P2. So this is just 1 over x1 minus x2 squared. We'll define this thing as P12, since it'll often show up. Okay, and so, for example, one thing you can immediately read off of this, because this is the only invariant you can write down with the right homogeneity properties, is that this operator and this operator have to have the same scaling dimension. It's homogeneous of degree delta in both P1 and P2. Yes? So I wrote this down for spin 0, so there's no z. We'll go to the spinning operators next. Was there another question? Okay, so let's do it. Now let's think about spinning operators. Sorry, so now my operator depends on P1 and Z1. Sorry, and then the second operator depends on P2 and Z2. And so now, okay, so it's a good start to write down P1 dot P2 to an appropriate power. But now we also need a numerator in order to contain all the spin dependence or the dependence on the polarization vectors. And that's, adding some extra numerator here is necessary in order for the 2-point function to have the right homogeneity properties rescale z. Okay, so it needs to go, if I take z to alpha z, it needs to go to like alpha to the L, where L is the spin. So I'm going to write down some numerator here, h12 to the L power. In my denominator, I'm going to write P12 to the delta plus L power, and the L, when I do my rescaling, P to lambda P, the L dependence is going to cancel between the numerator and denominator. And this H12 that shows up in the numerator needs to satisfy various properties. It has to be homogeneous of degree L in both z coordinates, and it needs to be transverse. And there's kind of a unique object which does this, which basically comes from taking dot products of the z's and p's in the right way. Okay, so I'm going to take z. Here I'm defining hij as zi.zj times pi.pj. This on itself, by itself, is not transverse. And so I need to subtract something off, which is pi.zj times pj.zi. Raise the blackboard, yes. So H12 is contains one Z1 and one Z2. And so to get the right homogeneity, I need to raise this to the L power, so that if I rescale Z1 to alpha Z1, I get alpha to the L. And if I rescale Z2 to alpha Z2, I get also alpha to the L. Okay? So this is basically the unique object that does that up to all the quantities that vanish, like, P1 squared vanishes, P2 squared vanishes, Z1 squared vanishes, Z2 squared vanishes, etc. Okay, so up to all those quantities that vanish, this is the unique structure I can write down. Yep. You need the two spins to be the same. Yep. Because this object is the same degree at Z1 and at Z2. And so that implies that the two spins are the same. And if you try to write down a different numerator that has different degree in Z1 and Z2, you're going to fail. Such an object doesn't exist with all these properties. I'm sorry?
If we have O, L1, O, L2, that would just be 0 if L1 and L2 are not.
Correct. That's right. Okay. So I think I'm out of time for today. So tomorrow we'll keep going and talk about 3-point functions. And we'll get to the point where we have a formalism to describe 3-point functions of three different spinning operators. And we can construct a basis for such 3-point functions. One of the components of that basis will be these Hij objects. And then we'll discuss basically all the different conformally invariant structures you can write down in the 3-point functions. And then that will set the stage for moving on to 4-point functions, where we can discuss the conformal bootstrap constraints of crossing symmetry, see the connection to conformal blocks, and so on. So thank you. I'll see you all tomorrow.